So last time we derived the equations for plane strain case. So today we are going to repeat pretty much the same process for plane stress case. Or maybe it's better say approximation. Because as we noted before, the problems are always really 3D, so these two-dimensional assumptions are basically approximations which would simplify the formulation, so we would be able to solve problems basically much easier. So how do we define plane stress? The assumptions are as follows. If we want to summarize the assumptions, basically the out of plane stress components are zero. So in the formulation here, we take the z-axis to be the out of plane axis. So the plane is defined basically by x and y axis. So the assumptions basically take this form. Sigma xx is generally not zero and will be a function of x and y, so independent of z. The same is true for sigma xy. However, sigma xz is going to be equal to 0. Similarly, sigma yy is going to be in general a function of x and y, non-zero. But sigma by z is going to be 0. And then sigma zz is also going to be 0. So out of plane components of stress are going to be 0. If you remember, when we were defining plane strain, we defined it using displacement. We said the out of plane displacement component is going to be 0. And then we derived the formulation. Here, plane stress, the definition is actually based on a stress, so the name kind of matches the definition a little bit better. So before moving forward, it is interesting to think whether the strain or displacement would be also independent of z. So basically the question is that we can ask is would basically the solution, which if you remember has displacement components, a strain tensor and a stress tensor, be independent of z. In plane strain case, we saw that this was the case. Basically, displacement was independent of z, strain the same, so was the stress. The question is, under plane stress assumption, can we say the same thing? Well, since stress is independent of z, and then since we are in the realm of linear elasticity, then it is very logical to assume that strain will be also independent of z. It turns out that displacement is in general, so not independent of z. So basically not having dependence on z for a strain doesn't automatically guarantee that displacement would be also independent of z. And this is kind of where plane stress and plane strain become a little bit different, and kind of this is where the approximate nature of plane stress formulation becomes a little bit obvious. So we get back to that a little bit later. So now we made these assumptions, we define plane stress. Let's, similar to plane strain, try to see what are the consequences of these assumptions. So let's start with here. Let's start with stress-strain relationships. So consequences. We first start with stress-strain relationship. Well, we are looking into linear elastic problem, and we already have defined the stress. So the easiest is to use the formulation of a strain in terms of a stress. So if you recall, for a linear elastic case, we simplified this relationship as Eij is 1 plus nu over E sigma ij minus nu over E sigma kk delta ij. So if we look at individual components, then Exx, again in the book, the author uses 1x instead of 2. I think that notation is a little bit confusing, so I encourage you not to use that and follow the notation that we use in the class. Would be 1 over E sigma xx minus nu sigma yy Exy is 1 plus nu over E sigma xy, and xz becomes 0 because sigma xc is 0. And then Eyy is 1 over E minus nu sigma xx plus sigma yy. Eyz is equal to 0, and Ezz is equal to minus nu over E sigma xx plus sigma yy, and it's not too hard to show that. Basically we can write it as minus nu over 1 minus nu Exx plus Eyy. So Ezz, first of all, is in general non-zero, and you can write it in planar stress case based on Exx and Eyy in terms of Exx and Eyy. So as we expected, our intuition told us before, all strain components are independent of Z. And this is kind of what you would expect because of linear elasticity. So only functions of x and y. Okay, so next let's try to look at strain displacement relationships. So well, hopefully you all remember the general strain displacement relation. So generally, if you all remember, then Eij is 1/2 Ui comma j plus Uj comma I. So if similar to planar strain, if we look at individual components, then we are going to have Exx U comma x, and again remember that just write it down here, that the displacement vector here, we basically take it to be U V W. So don't be confused about using U for the displacement vector and also the X component of U. So we follow the book notation in here. And in general, we still don't know, u could be a function of x, y, and z. We don't know, right? exy is 1/2 u comma y plus v comma x. E y y v comma y. So again, we still don't know. So in general, v also can be a function of x, y, and z. And then the components which have z in them. Let's look at them. E z z is w comma z. In general, w is also a function of x, y, z until we know more. We saw that it is non-zero. So if you look back, generally non-zero. But then the other two strain components which have z in them, we saw that they are 0. So exc is 0. However, if we write it in terms of displacement, it is 1/2 u comma z plus w comma x. So EYZ again, we saw that in the previous panel, we saw that this is 0, and if you write it in terms of a strain, it would be 1/2 V comma Z plus W comma Y. And these last three equations, basically, they give us some differential equations which are not trivial. So now we can examine these three and try to see what we can say about displacement. Okay, let's start with a simple one. EZZ. Well, recall that EZZ, we could write it as basically a combination of EXX and EYY multiplied by elastic constants. And since EXX is only a function of X and Y, and so is EYY, EZZ, it follows that EZZ will be also only a function of X and Y, because you can write it in terms of them. So on the other hand, we know that EZZ is W comma Z. So if we integrate since EZZ is not a function of z is it is a constant, so we can basically conclude that w would be a function which is linear in z. So w would be easy z times z plus some arbitrary function of x and y. So basically this is important. The out of plane displacement component is a linear function in z, as you can see here. So I write this down here. So the out of plane component of displacement is linear in z, which means that it's not independent of z, but we know that it is linear. And now that we have w, we can look back and look at, for example, exc since this is equal to 0, we know that u comma z plus w comma x is going to be 0. So if we substitute for w, so u comma z would be ezz comma x z plus f comma x. So I'm just substituting w from above. So we have now an expression for u comma z. So if we integrate, we see that u is a function of u is not independent of z, and the dependence is on z squared. So if we follow the same procedure for yz, we find that we can say a similar basically statement for v. We write this here. So if you look at eyz, we'll see that v will be also depends on z squared. So basically the bottom line here is that the displacement components U, V, and W are non-trivial functions that in general depend on Z, are in general dependent on Z. So in other words, the displacement is 3D, it's three-dimensional. So although this is planar stress, we see that unlike planar strain, not everything is going to be confined to a plane. The displacement is basically really a function of Z. And now, because of that, in the next series of equations that we are going to derive, you see that this makes some of the equations not to go to zero, and then we have to make assumptions, and that's why the planar stress formulation is approximate. We didn't have these issues when we talked about planar strain case, which is mathematically exact. So let's look at the equilibrium equations next. So I hope that you all remember the Cauchy law by now by heart, so you can just write it down. I write it down quickly without looking at me. So equilibrium equations. So the general form is sigma ij comma j plus fi equal to 0. So this gives us three equations. So let's write them down. So sigma xx comma x plus sigma xy comma y plus sigma xz comma z plus fx is equal to 0. Sigma yx comma x plus sigma yy comma y plus sigma yz comma z plus fy is equal to 0. Sigma zx comma x plus sigma zy comma y plus sigma zz comma z plus fz equal to 0. So let's cross out the terms which are 0. The out of plane stress components are 0, so we very fast we can say that all of these terms are 0. So here, similar to planar strain case, Fz has to be 0. So the out of plane component of the external body force has to be also 0 in plane stress case. So this would be similar to planar strain. Now let's look at the displacement formulation. And Navier equations. Again, the equations have the general form of mu, Laplacian mu, plus lambda plus mu, Zolame constants, plus f equal to 0. Now, these are also three equations. Let's write them down. It would be a good practice to write it for yourself. It's always good. Last time you saw how the Laplacian looks like in index notation. U comma yy plus u comma zz plus lambda plus mu. Here we have basically the gradient of the divergence. So we have v comma y plus w comma z, then comma x plus fx equal to 0. The second is pretty similar. So we have v comma xx plus v comma yy plus v comma zz plus lambda plus mu u comma x v comma y w comma z, this time comma y plus fy equal to 0. And then mu w, since it's not 0, this third equation also exists. We saw that the out of plane displacement w is not necessarily equal to 0. Wyy plus wzz plus lambda plus mu, again u comma x plus v comma y plus w comma z, and now partial with respect to z plus fz equal to 0. Now see, let's look for the components that are 0, we know. So the assumption is that fz has to be equal to 0. This we know. What else we can say here? Well, we learned that also w is generally non-zero, but it's linear in z, so the second derivative with respect to z will be 0, right? How about here? Similarly here, so the second derivative will be also 0. So this term here will be reduced to basically just u comma x plus v comma y comma z. Anything else here? 0? Well, not really. but we can make a little bit of simplifications to make the form a little bit more elegant. And this is as follows. So what we are going to do is we're going to use the relationship between EZZ, EXX, and EYY to write W comma Z in terms of U comma X and V comma Y. So we call that we said this before, that EZZ, which is W comma Z, can be written in terms of EXX and EYY, and these are nothing else but U comma X and V comma Y. So if we substitute substituting for W comma Z, in Navier equations, above, we can have a little bit more elegant looking equations. So let me write them in the next panel. So that will be the form they would take. So then we have Navier equations for plane stress. And then we have mu, Laplacian mu plus lambda plus mu 1 minus 2 nu over nu U comma X plus V comma Y comma X plus Fx equal to 0. That's the first one. And then we have mu Laplacian V plus lambda plus mu 1 minus 2 nu over nu U comma X plus V comma Y plus Fy equal to 0. So you may ask what happened to the third equation. So in plane stress, we basically conveniently forget about the equation in the z direction. So we basically ignore the equation in the z direction. So you saw that the out of plane displacement component is not generally zero, and generally displacements, they are the components of displacement they actually depend on z. So which makes the problem three-dimensional. The theory, to make things simpler, we just forget about some of these terms, and this is a main difference between plane stress and plane strain. And plane strain mathematically is clean and exact. If the assumptions are satisfied, the mathematical description is exact. Plane stress is approximate. So I just write this down here because this is important. So basically the assumption that we are making is that the variations in the field variables in the z directions are so small that we can neglect them. So we just neglect them and we move on. Now it is worth looking at the Navier equations for plane strain case again and make a quick comparison. So recall that the Navier equations for plane strain case. So we have mu Laplacian u plus lambda plus mu u comma x plus v comma y comma x plus fx is equal to 0. Mu Laplacian v plus lambda plus mu u comma x plus v comma y plus fy equal to 0. If we compare these two sets of equations, which is one for plane stress, so the two ones that we actually retain, so plane stress and here is plane strain, we see that the equations, the forms are very similar, and the only difference is basically the coefficients here. So here we have lambda plus mu for plane strain, and for plane stress we have lambda plus mu times 1 minus 2 nu over nu, which this can actually be simplified to e over 2 1 minus nu. So solving a problem would be exactly similar if we just switch the elastic constants when we go from plane stress formulation to plane strain. or vice versa. Okay, so now let's look at the strain compatibility equations. So last time we looked at the strain compatibility equations for plane strain, and you saw that most of them, they are trivially satisfied. 0 is equal to 0. One of them, you guys yourselves, you actually showed that, and the ones and which they're not trivially satisfied, they are reduced to one equation. So let's see what will happen here. So strain compatibility equations. Now we are plane stress. So if we take, for example, ij as xx, it turns out that the compatibility equation will be exactly the same as what we got for planar strain case. So yields the same equation as in the plane strain case, which, if you recall, was exx comma yy plus eyy comma xx equal to 2exy comma xy. So however, not all the strain compatibility equations are trivially satisfied. So, for example, we are going to look at the case where ij is equal to zz. So, however, not all other equations are trivially satisfied, which was the case in planar strain. For example, let's take ij equal to zz. So if we write the terms, so ezz comma xx plus ezz comma yy plus ezz comma zz plus exx comma zz plus eyy comma zz plus ezz comma zz, and then the other two terms will be exactly the same, so we have minus 2 exc comma xc minus 2 eyz comma yz minus 2 ezz comma zz. So these three terms, they will go to 0. Let's see what else is 0. So exx and eyy, these are function of x and y, so this is equal to 0, this is equal to 0, and exc and eyz are also 0. So what we get is ezz comma xx plus ezz comma yy equal to 0, and as you can see, this is non-trivial because ezz, we saw previously that you can write it in terms of exx and eyy, so it's a function of x and y, and it may and the second derivatives may indeed be non-zero, so this is non-trivial. However, again, in plane stress, we somewhat forget about the equations, the compatibility equations that do not go to 0 trivially, and just retain the equation, the first one, which is similar to plane strain. So this is another approximation that we didn't have in plane strain, but we have it in plane stress. So we forget about those strain compatibility equations which are not trivially satisfied. And only retain this equation, which we wrote earlier, exx comma yy plus eyy comma xx equal to 2 exy comma xy, which is similar to the one in plane strain case. Okay, perfect. So the only remaining equation now is basically the stress formulation. Let's look at that equation too. And if you remember, that is the Beltrami-Michel equation. Michel, actually. That's the correct pronunciation. It's a British name. A stress formulation Beltrami Michel equation takes the form Laplacian sigma xx plus sigma yy is equal to minus 1 plus nu fx comma x plus fy comma y. So for plane strain, the equation was of this form. If we compare these two equations, again, the only difference is these coefficients, which are the elastic constants in front of fx comma x plus fy comma y. So just like the Navier equations, then we can say the formulations in plane stress and plane strain are the very same, except for a switch basically of the coefficients, which are basically a function of the elastic constants. In fact, if Poisson's ratio would be 0, the equations become exactly similar. So now that we have the formulation for plane stress, just like plane strain, we kind of have to reverse engineer and say, okay, what is the physical implications of this definition and this formulation? So basically, what kind of a problem can be approximated reasonably well using plane stress formulation? So the kind of problem that you want to have considering the approximation is that things do not change much in the z direction. So if we want that, we won't have any stress components in the z directions, and things do not change much in the z directions because we ignored a bunch of equations. The only possible solution would be having a kind of plate, like a structure where the thickness is going to be much smaller compared to the other dimensions. So if we take, for example, this plate, and if we take basically x, y, z here, and then consider a mid-plane section which basically cuts this in half. We want to make sure that first of all we won't have any out of plane stress, so that would mean that we won't have any stress components basically on the top or bottom surfaces, so they have to be traction free. So basically you want to have at the top and bottom at both surfaces, what we want to have is sigma zz equal to 0, sigma xz equal to 0, sigma yz equal to 0. And then we don't want to have any out of plane stress in any of the slices that we take at any z, that at any slices that we take, any z slices. So for that we want to make sure that this plate is really thin, because you saw that this is not really the case, so you are still going to have the other components. Just to make sure that they are very small and negligible, you want to have a very thin plate. Basically 2h, the thickness, let's just call it thickness. The thickness should be much smaller than the other dimensions. So if we have these conditions, then we can use plane stress to approximate a problem like this. So this is where I stop. Then we start basically with the solutions, a little bit about generalized plane stress, and with the solutions on Tuesday, and I think that the class will start with a small one question quiz on plane strain and plane stress, and then we look at generalized plane stress and then area stress functions. Well, then I see you on Tuesday.